Have you ever wondered what you really see when you look up at the sparkling night sky? Those stars and distant galaxies are not images of the present, but fragments from the distant past. The light from the Andromeda Galaxy, our nearest neighbor, took 2.5 million years to travel across the vastness of space to reach your eyes. Imagine, the light you see today began its journey before humans even appeared. Even the light reflected from Jupiter, the giant planet in the solar system, takes 30 minutes to reach Earth. And objects closer to us? They never show us images right now. But what makes the light from the beginning of the universe so special? It is it that reveals the secret of the Big Bang, the moment when everything was born. The oldest light scientists have ever recorded came from when the universe was just a few 100,000 years old, a newborn in its billion-year history. This light, like a cosmic diary, tells the story of those early days, when everything was chaotic and mysterious. But what caused the Big Bang? Was the universe sleeping in a state of quiet stillness before some event woke it up? Or did our universe collide with another universe, causing a great explosion? Perhaps the universe is just part of an eternal cycle of explosions and contractions? And why was the early universe invisible? How does energy shape time? And why is 97% of the observable universe forever beyond our reach? Could all these mysteries point to another Big Bang in the future? To trace the origins of the universe, scientists point giant telescopes to the farthest corners of space. When they record light from galaxies billions of light years away, they are not just collecting light, they are tapping into the past. That light, like a messenger from the distant past, began its journey when the universe was very young. Because light takes time to travel through space, and because the universe has been expanding since its birth, the journey of these rays of light is also stretched, like a silk ribbon stretching out through time. But there is a limit. We can only look back so far. The first photons, the primordial particles of light, could not move freely through the young universe. They were trapped, constantly colliding with free electrons, making the universe at that time like a thick fog, completely opaque. Then, about 380,000 years after the Big Bang, as the universe cooled, these photons were released. They began their epic journey, heading in the direction they had started. Over billions of years, the wavelength of this light was stretched so far that it shifted from visible light to microwaves, creating what scientists call the cosmic microwave background, a precious relic from the earliest times. Everything before that? Completely beyond our view, a mystery locked in darkness. To understand what happened in the early stages, scientists have to rely on predictive models. As time goes on, entropy, the disorder of energy in the universe, keeps increasing. Simply put, energy gets more and more dispersed, becoming less and less usable. Stars explode into supernovae, black holes slowly evaporate, hot things cool, and even cold things get warmer. Entropy, as an immutable law, shapes the way we understand time. The future is a more dispersed state of energy, while the past is a more concentrated, compact one. But why does entropy determine the direction of time? That is a question that still puzzles scientists. Some physicists theorize that before the Big Bang, the universe may have been in a state of hibernation, small and quiet for an eternity. Then, at one fateful moment, a mysterious push woke it up. This state, called a false vacuum, seems stable but is actually as fragile as a ball perched precariously on a mountainside. Imagine a peaceful valley between towering mountains. The people in the valley may think it is the safest place, but with just the slightest vibration, everything could collapse, opening a new chapter for the universe. So what happened next? The mysteries of that fragile state lead us to larger, deeper questions about the nature of the universe and its journey. Imagine a peaceful valley, nestled between towering mountains, where everything seems still and eternal. But deep below, an underground river flows silently, carrying every pebble out to sea. Day by day, the ground weakens until one fateful moment, the entire valley collapses with a deafening bang. That's how we imagine the universe before the Big Bang, a seemingly stable but fragile false vacuum state, just waiting for a kick to explode. But what caused the universe to awaken from that deep slumber? In the magical world of quantum mechanics, where tiny particles dance according to unpredictable rules, anything is possible. If the early universe followed the laws of quantum field theory, then a random event as small as a spark could have triggered the transition from the false vacuum state to a truly stable state. Imagine a ball floating on a mountainside, and with just a slight breeze it would roll down, causing a massive landslide. That was the moment our universe began its epic journey, the Big Bang. It has long been thought that the universe began at a singularity, where all matter and energy were squeezed into an infinitely small space. But modern science paints a different, more compelling picture. Instead of a singularity, the universe began in a cold, empty space so small that it was only 100 billion times the size of a proton. But don't let the size fool you. Inside that tiny space is a huge source of energy, creating pressure so strong that it creates an inverse gravitational force, a push rather than a pull. It was this push that caused the universe to undergo a period of cosmic inflation, where it doubled in size by more than 80 times in the blink of an eye. Imagine a bomb about to explode. Initially, the material inside begins to decompose, creating hot gases and releasing energy. The pressure builds up, pushing against the bomb walls, and then, boom, the explosion occurs. Likewise, the energy released during inflation is released into space, heating the universe and creating countless subatomic particles. From a tiny speck of dust, the universe has expanded to nearly an octillion times its original size, in a grand dance of creation. But what happens when the energy that was once tightly concentrated is now dispersed throughout the vastness of space? That's the story of entropy, the tendency for things to move from order to disorder. Have you ever wondered why today's universe, with its magnificent clusters of galaxies and exquisitely arranged star systems, is considered more disordered than the hot mess of early particles? Think of the Big Bang as a confetti cannon. When you pull the string, the colored pieces of paper come apart, and they should be scattered everywhere. Instead, they arrange themselves into perfect shapes, circles, squares, triangles, representing subatomic particles, atoms, and molecules. Amazing, right? Even more amazing is that the universe seems to be the same in every direction. No matter which direction scientists look, they measure an average temperature of about 2.7 Kelvin, a mysterious consistency. This shouldn't be the case, because the universe is about 13.8 billion years old, but the diameter of the observable horizon is 92 billion light-years. Space is expanding faster than light, stretching the distances between distant regions so that they can't communicate to achieve this uniformity. So what makes the universe so harmonious? Imagine standing before a giant painting, where each drop of paint represents a distant region of space. No matter which angle you look at it, the painting appears to have the same hue, the same temperature, about 2.7 Kelvin, cold and uniform. But how is this possible? How can 2 points more than 14 billion light-years apart, never having had the chance to communicate because of the speed of light, have the same average temperature? This is the horizon problem, a puzzle that has puzzled scientists. And then there is another mystery, the flatness problem. According to Einstein's theory of relativity, massive objects like stars, galaxies, or black holes warp space-time, creating ripples in the cosmic fabric. But when viewed at a larger scale, those ripples seem to disappear, leaving the universe as smooth and flat as a still lake. How is this possible? A fascinating hypothesis has emerged: eternal inflation. Imagine a giant, entropy-filled parent universe that expands forever. But somewhere along the line, the expansion pauses, and daughter universes, tiny bubbles of low entropy, are born, separate from each other. Are these daughter universes being created over and over again, like flowers blooming in an endless field? The Big Bang we know may not have been the beginning of the entire universe, but rather a single momentary explosion in a daughter universe, triggered by tiny quantum fluctuations in a much larger picture. Each daughter universe, like a unique snowflake, has its own characteristics and its own constants of nature. Some may be cold and empty, while others, like ours, seem perfectly tailored to foster life. Stars burn, creating essential elements. Galaxies rotate in harmonious dances. But are we just one of an infinite number of universes, where every possibility is tested? Or is the answer simpler, that there is no need for parallel universes? Alan Guth, one of the most brilliant minds, proposed that cosmic inflation did not occur steadily. In the early stages, when the universe was smaller than a speck of dust, regions of space now billions of light years apart were close enough to chat and exchange matter. Then, in a flash, the universe doubled in size by more than 80 times, faster than the blink of an eye, before slowing down and expanding at a more steady pace. It was this inflation that stretched everything, creating the uniformity we see today. But did you know? Even now, the universe is expanding at a dizzying rate. If we sent a probe traveling at the speed of light into space, it would only be able to explore about a third of the observable horizon, 3% of the total volume of the observable universe. That means that 97% of the observable universe is forever beyond our reach, like mysterious lands on a map that has never been drawn. Our observable universe is just a tiny drop of ink on a much larger cosmic canvas. In this small corner, everything seems uniform, flat, and at the same temperature. But is the entire universe really the same? These questions, like stars in the dark, invite us to continue to explore. Is our universe part of a larger picture, where the laws of physics change in ways we have never imagined? Imagine standing on a hill, looking at the gentle curve of the Earth. From this small perspective, everything looks flat, but when you look further out, you see the planet's hidden curves. The same is true of the universe. Our limited perspective can hide huge changes. Before inflation, the early universe may have been full of temperature differences, like a patchwork of light and dark. But as inflation unfolded, stretching space at breakneck speed, those differences were pushed so far apart that they were no longer visible to us. Or has inflation flattened the universe, like a tiny ball in your hand, where even the mighty Mount Everest seems so smooth as to be non-existent? The idea of eternal inflation has many scientists puzzled. If each subuniverse has its own physical laws, does it make sense to study the particles and laws of our own universe? Instead, another theory is gaining traction: the cyclical universe. Think of the universe as a dancer, constantly repeating a dance of birth and destruction. Each cycle begins with a big bang, a brilliant burst of energy that ushers in a new era. Galaxies glow, stars burst into flame, and complex structures form as the universe expands and matures. But then a mysterious figure steps onto the stage: dark energy. Its strange repulsion quietly takes over, causing the universe to expand faster, overcoming the pull of gravity. Eventually, as dark energy takes over, everything is pulled into a big crunch, a dramatic collapse where the entire universe collapses into a tiny, hot point. But the story doesn't end there. From the ashes, a new Big Bang erupts, starting a new cycle, like an eternal cycle of creation. Some physicists believe that the Big Crunch did not require the universe to collapse completely. As space contracted, the observable horizon, the boundary we can see, shrank much faster, turning the universe into a tiny point. Imagine you were standing in a large room, but the walls began to close in. First, distant galaxies disappeared from view, then the stars in the Milky Way, then Mars, then the Moon. Eventually, even the objects in your room, and then you, disappeared from view. Everything became isolated, like dust particles floating in space, no longer interacting with anything around it. The universe fell into a state of stillness, frozen in time and space, until a new cycle began. But did the universe actually dance to this cyclical tune? That depends on the curvature and density of space. If the universe is filled with matter and energy, the combined force of gravity could curve space-time into a spherical shape, like a sheet folding in on itself. This curvature would slow down the expansion, and perhaps even go so far as to reverse it altogether. Everything would collapse in a big crunch, where galaxies that were once scattered across the vast expanse of space would be squeezed into a tiny point. But what if the density of matter is not high enough? This question opens a new door, leading us to deeper mysteries about the fate of the universe. Will our universe continue to expand forever, or will it one day collapse to begin a new chapter? Imagine the universe as a giant sheet of fabric, not flat but curved into the shape of a saddle, where gravity is too weak to restrain the violent expansion driven by dark energy. In such a universe, all matter is stretched, flying away at ever-increasing speeds, causing space to expand forever, never stopping. But what happens when the universe keeps growing like that? It is this constant expansion that opens a new door, leading us to a fascinating hypothesis: brain cosmology, based on string theory. Have you ever thought that our universe is just a page in a great cosmic book? Imagine the whole of existence as a giant book, where each page is a brain, a flat universe with its own unique physical laws. These brains float, sometimes colliding with each other, in multidimensional space. Each time they collide, a huge explosion of energy erupts, blazing like a great furnace, creating a huge explosion, the Big Bang, that gives birth to a new universe. Our universe, at 13.8 billion years old, may have been the result of just one such collision. Back then, everything was hotter, denser, like a speck of dust containing all the potential for life. But what happened to the universe immediately after that explosive moment? Let's go back in time to a period called the Planck epoch, the earliest moment that modern physics can reach. Imagine a photon, the fastest particle of light in the universe, traveling at the speed of light over an impossibly small distance. The Planck length, 1.6 x 10 superscript 3 meters. The Planck time is the short time it takes this photon to travel that distance, just 100 million trillion trillionth of a second after the Big Bang. It is the edge of our understanding, where the laws of physics seem to intertwine in a chaotic dance. During the Planck epoch, the entire universe was the size of a speck of dust, billions and billions of times smaller than a photon. The temperature? Incredibly hot, 10 superscript 3 superscript 2 degrees Kelvin, far exceeding the searing heat inside the core of a neutron star after a supernova explosion. At this temperature, particles move wildly, vibrating with intense energy, creating something called a quantum foam. Imagine a boiling ocean where microscopic black holes and wormholes appear and disappear in an instant, like soap bubbles popping in the blink of an eye. Everything is chaotic, unpredictable, like a cosmic painting being painted with random brushstrokes. Immediately after the Big Bang, for a brief moment called the Grand Unification, the universe was a blazing furnace of energy. All the fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were combined into a single force that dominated all of space. But how long did this phase last? A mere 10 superscript 3 seconds after the Big Bang, a blink of an eye in cosmic time. That was when the universe was a seething sea of energy, where everything was still taking shape. These first moments, like the opening notes of a great symphony, laid the foundation for everything we see today. But what happened as the universe began to cool, when the forces separated and particles began to form? Imagine the young universe as a giant furnace, where the fundamental forces of nature began to separate, like dancers leaving a group dance to begin their own performance. First, gravity stepped out, asserting itself as an independent performer, setting the rhythms of the universe. At this point, the energy in the universe reached an incredible level, 10 superscript 2 electron volts, trillions of times more powerful than what our most advanced machine, the Large Hadron Collider, can produce. Can you imagine that power? A cosmos seething, pulsing with pure energy, like an ocean of fire waiting to be shaped. As the universe cooled, the strong nuclear force separated from the others, ushering in the particle age just 10 superscript 1 superscript 2 seconds after the Big Bang. Then the electromagnetic force and the weak nuclear force separated, like the final pieces in a chaotic puzzle. Then a special player came along, the Higgs field. From this field, the Higgs boson was born, acting as a potter, giving mass to elementary particles like quarks and leptons. The temperature of the universe was still blazing hot at 10 superscript 1 degrees Kelvin, but it was slowly falling. It was the Higgs mechanism that shaped the first bricks of matter, laying the foundation for everything we see today. Somewhere in this chaotic period, a mysterious event called baryogenesis took place. No one knows exactly when, but when the universe was so hot that particles were traveling at nearly the speed of light, particles and antiparticles collided, destroying each other in tiny explosions. But something miraculous happened. Matter outnumbered antimatter by a tiny margin, just one extra proton for every billion antimatter particles. It was this delicate imbalance that created a matter-dominated universe, paving the way for stars, planets, and even life. Just a millionth of a second after the Big Bang, as the temperature dropped to 10 superscript 1 degrees Kelvin, quarks began to combine, forming protons and neutrons, the basic building blocks of atoms. About 3 minutes later, the universe cooled to 1 billion degrees Kelvin, ushering in the age of nucleosynthesis. During this brief period, light atomic nuclei like hydrogen and helium formed, the first seeds of future stars and galaxies. These nuclear reactions laid the foundation for stellar processes, creating heavier elements and paving the way for the formation of planets. Then, about 380,000 years after the Big Bang, the universe cooled to 3000 Kelvin. At this point, the first molecule, helium hydride, was born, marking the transition from simple atomic matter to chemical complexity. Imagine, from a sea of chaotic particles, the first chemical bonds appeared, like the first notes in a cosmic symphony. Electrons began to bind to nuclei, releasing photons that traveled freely through space. The universe became transparent, like a veil of mist lifting, allowing the first light to illuminate its history, so that billions of years later, humans could look back in time. Over the next billion years, another mysterious element emerged: dark matter. It did not emit light, it was invisible, but its gravity quietly shaped the universe, pulling galaxies together and creating vast webs of space. So what happened as the universe continued to expand and grand structures began to form? Hey tuong view true nu mot buk tran kong lo, noi moanet villa mot ngoi sa, mot thien ha, hey mot han tin. And hung in sao trong buk tran I la hai nan tabian, nu and hung bong ma lang la din hin moi Thursday, vat chat toy van nong luong toy. Kak na vat ly cho rang vat chat toy, du vio hin va kong fat ra on sang, lai nong gap sao lon vat chat thong thuang ma chung ta thay, tu and hung goi sa lapland den chin ko the ban. Trong kai du, nong luong toy, mot lu ky bi kong kem, bat dao chiem u the catch day koang nam den sao tai nam, tuk de view true john no voi talk du gate song in han. And hung luk nai la gi? Chung den tu dao? Du chung taden in engwak vi qua ku exe zoi qua view true, ben chat qua vat chat toy van nong luong toy van la mot ka du chua ko loi jai, nu mot ko bao view true dang cho dua kemfa. Hu beat vi qua ku kong chi jup chung ta vi lai han trin qua view true, makan mora mot kan quada ngo nin tuong lai. Ban ko bao geo tu hoi so fan qua view true sera sa? Kai dung ona ri qua thoi jan, chung ta kong koi by quan hut boi in hung bien fia truok. Lu view true se dan ton lui trong mot tsai chet and hiat m dem, noi moi nong luong fan ton, de lai mot kong john lan leo, tin lang? Hey nong luong toi se dan dat view true den mot kich ban du doi han, mot view exelon, big rip. Noi moi Thursday, tu thien ha den gwin tu, by xe tok trong mot tsai ket de kich tin? Hey tuong kakangoi sa xe zoi tan bien. Kak thien ha by kio john nu and hung soi chi, va koi kung, chin kong john by xe nat. Lu du ko phi la din men qua view true chung ta? And hung ka hoi nai kong chi la by ton cho kak na qua hok, makan la loi moi goi den tri tuong qua tat ca chung ta. Vu true, voi tat ca vdp va bien qua no, dang kremoti ka chuyen dai hung tai nam, va chung ta chi lin hung nen chung no bi trong mot chuang non engui. Han trin kam fa qua ku va tuong lai qua view true kong chi jup chung ta hu vi angwan ga qua min, makan koi de sutamavi and hung gi dang cho doi fia truok. Ve du gi nam o chuang tip theo qua ka chuyen view true nai? Lu chung ta ko the tim ra man moi de jai ma ban chat qua nong luong toi, he kem fine hung bi and moi vi catch view true se ket tuk?